All right. Good morning, guys. Thanks for waking up bright and early to come and just see me. My name is Kevin McGee, and I am the production lead at Radiant Solutions. And today I'm going to be giving the talk called An Eye in the Sky, How Radiant Solutions Processes Satellite Imagery with AI and Amazon Mechanical Turk. So did anyone get a chance to catch the keynote yesterday where our CTO, Walter Scott, talked about machine learning and AI on satellite imagery and disaster recovery and things like that? If you did, I'm going to try to give you a little peek behind the curtains of how all that magic actually happens. So just a little bit of company history. We recently went through a merger with MDA. So what we did was we took Digital Globe Radiant, which was Digital Globe's information sector, and we took MDA Information Systems, which was MDA's information sector, and we actually combined those two to create Radiant Solutions, which is now our new information sector. And now we're all under the umbrella called Maxar Technologies, and it's pretty awesome. We actually have a full suite of space technologies. SSL actually manufactures satellites, so we can go to them to manufacture our new satellites coming up soon. We have Digital Globe that actually operates the satellites in space and takes a pretty imagery of the Earth, and we have Radiant Solutions that does all the analysis on the satellite imagery. So a little bit about myself. Like I said, I'm the production lead at Radiant Solutions. I've been working on the machine learning team for about a year and a half, and I'm in charge of the overall infrastructure of our machine learning projects. So specifically the data generation portion, the AI training portion, and the AI integration portion. But specifically today, I'm just going to be talking about the data generation portion. Basically, how do we do this at scale? So we're generating millions and millions of labeled images, and how do we do this at high quality, high enough quality to generate a decent enough machine learning model? So a little bit of overview of what I'm going to be talking about. I'm going to talk about how we use machine learning to process satellite imagery, and specifically how we utilize Amazon Mechanical Turk to generate the data that makes it possible to create those machine learning models. And I'm going to try to give this talk at a beginner level, so everyone can try to understand from the start to finish exactly how this works. So I'm going to give a little overview of how machine learning models work on imagery specifically, and then how we apply that to actually using satellite imagery. So just a little overview. I'm going to talk about the problem scale. How big is this problem? Talk about the relationship between machine learning and imagery. Then I'm going to talk about our crowdsourcing platform called Tomnod. I'm going to talk about generating data with Mechanical Turk and Tomnod for machine learning, and then I'm going to close it off. Okay, let's talk about the problem scale. It's a pretty big problem. We use Digital Globe imagery for our machine learning, and Digital Globe has 5 Earth observation satellites on orbit, and every single day they take 3 million square kilometers of imagery. And just to give you a context on that number, that's the entire country of India. And they have the highest commercial resolution available, which is extremely important to us because the things that we're interested in are the objects in the satellite imagery. So we're looking for things as small as cars to as big as buildings. So the resolution is incredibly important to us so we can actually detect those small objects. So here is an image taken by Digital Globe. It is a shipping port in Venezuela. And what we want to do with this image is some kind of analysis on the change that's going on in the image. So we want to know, did the shipping containers increase or decrease? Did the ships in the actual port increase or decrease? What kind of vehicles are we seeing in the area? Did that increase or decrease? So what we can do today is we can hire an imagery analyst or multiple imagery analysts, and they can come in and they can start counting one by one the shipping containers and the ships and the vehicles, and after a couple of days they can generate a report that's useful and has actionable insight. This is good, but it's slow, so what if we could use machine learning to automatically translate the image to this? Increase shipping activity in this location. So what we would do is we would take our machine learning model, and it would count the shipping containers, it would count the ships, it would count the vehicles, and take in comparison from an image taken beforehand and see what kind of change are we seeing in the imagery. And then that way we could take this information and point out to the imagery analysts and say, hey, there's something interesting going on at this shipping port. You should probably take a look. And this is really the direction we need to go in. If we look at this quote from Scott Curry, who's the NGA mission director, he says, if we looked at the proliferation of new satellites over time, and we continue to do business the way we do, we'd have to hire 2 million more imagery analysts. So it's just not going to scale with people, so we got to get machine in the loop. So let's talk about the relationship between machine learning and imagery. So here's how it works in the research and development world. We have a rabbit in a hat, and we have a bunch of images of rabbits in a hat, and someone goes through and actually goes through all those images, and they tag this image has a rabbit in a hat here on this image. And then we take thousands of those labeled images, and we feed it through what's called a neural network. And basically, a neural network is the computer's representation of a human brain. And then after it gets all that imagery and gets fed into the computer, it creates what's known as a model, or a computer vision model, of a rabbit in a hat. So we could take that model and run it over new imagery, and the computer can now say, there is a rabbit in a hat in this image, or there isn't. So that's cool, but rabbits in a hat, not super useful. So here's how we use it at Radiant Solutions. We take our big imagery that we take from our satellites, and we actually go through and label the areas of interest. So let's say in this example, we're trying to label all the ships in a port. And we take those labeled images, and we chop them up, and we feed them into a computer, into a neural network, and create a model that can actually learn what a ship looks like in a shipping port, and then we can just run it over new imagery and automatically detect new ships and new imagery. So there's a lot of machine learning and ground imagery examples out there. There's 3 image competitions that are publicly available data sets that have things like people labeled in imagery, or kites, or beaches, or whatever, but it's all ground imagery. People have their phones, they take pictures, and there's a ton of them. There's ImageNet, there's Pascal VOC, there's Microsoft Coco, and so the world of ground imagery and machine learning is pretty advanced because there is a lot of publicly available data out there. And we can see a lot of advanced industry examples. Autonomous vehicles is one of them. Obviously, that has to be very advanced, so your vehicle doesn't see a person and hit it because it didn't detect that it was a person. There's also Facebook facial recognition. So if you've ever uploaded a picture to Facebook, and it will automatically tell you, hey, is this you in this picture? That's because on your older pictures, what you've been doing is if you've tagged your face in one of your older pictures, you're actually labeling images. And then what Facebook does is they automatically create a computer model of what your face looks like, so that when you upload new imagery to Facebook, it can run the model over the new image and automatically detect that Bob is now in this image. So how do we apply machine learning to satellite imagery? Well, we're starting off with classifiers. So a classifier is basically running a model over a portion of satellite imagery and determining what type of land is there. So is this a rural area? Is it urban? Is it water? Is it forest? Just trying to determine basically a broad sense of what we're looking at on the Earth. More recently, we've been using what's called a detector. So instead of just classifying a piece of land, what we want to do is say, there is an object of interest located here exactly on this image. So we're looking for detecting things like planes or trains or boats or cars or anything that would be interesting to a customer. So let's talk a little bit about Tomnod. Tomnod is our crowdsourcing platform. Essentially, what it does is it takes our satellite imagery and it serves it to a crowd of people. And it has tools in there that allow you to tag the satellite imagery, create those labeled images that I was talking about. And essentially, we need 3 things to make a really good model. First of all, we need the location on the Earth. So basically, the XY coordinates or the lat-long coordinates of where that object actually is on the Earth. And then we need the object type. What type of object it is. Is it a car? Is it a plane? Is it a train? Things like that. And then we need a ton of examples. So we need to find a way to scale this problem because we don't have those publicly available data sets out there for people to use. So we need to go in and actually create the training data ourselves. So let's talk about the relationship between Tomnod and Amazon Mechanical Turk. We use Amazon Mechanical Turk to help scale this problem. Like I said, we don't have any data already generated, so we have to find a way to do that. And essentially what Amazon Mechanical Turk does, it's a scalable, on-demand workforce that we can call upon to bring people to the Tomnod platform, and they can start looking at our satellite imagery. So we need massive amount of training data quickly, we need it timely and cost effectively, and so Mechanical Turk was just a good fit for this. So essentially the way it works is that we have Tomnod, which is our platform that serves satellite imagery. We call upon Amazon Mechanical Turk crowd to come to Tomnod to start labeling our imagery, and then what we get is meaningful data out of this. So here is an example of what Tomnod looks like. This is just after Hurricane Maria struck Puerto Rico, and we were looking for things that could be useful to people, first responders on the ground. So we're looking for things like trash heaps or flooding or damaged buildings, things like that. So what we would do is we would post this on social media or whatever to have people come to Tomnod, and they can start looking through the imagery and trying to find these things, and then we can get that information to the first responders on the ground. And this is good, but unfortunately it's slow. So what if we could do machine learning? So we could call on Amazon Mechanical Turk to come to Tomnod to massively scale this problem, to look over all the available imagery we have of Puerto Rico or any other hurricane disaster or any other earthquake disaster, whatever we're interested in, and they can come through and label all this stuff, and then we can create a machine learning model, and we could do this so much more quickly and get the information to the first responders on the ground way more quickly. Another thing you can do in Tomnod is what's called the validation campaign. So we have an already existing data set, and we want to actually increase the quality of that data set. So one of the things we could do is we can feed information into Tomnod saying this box is labeling a aircraft, and we want to know more details about that aircraft. We want to know, is it a small aircraft? Is it a passenger aircraft? Is it maybe not an aircraft and it's an error in the data set? We can use this as a way to increase the quality of the data set. And there's a bunch of different options that you can validate on. So the example I showed before was existing data. If you already have an existing corpus of data, you can just feed that into Tomnod and hopefully get higher quality data sets out of it. Another thing you can do is go to open source venues. So OpenStreetMap is super popular, GIS, crowdsourced, labeled map website. And what we could do is we could take objects that are already labeled in there and also feed that through Tomnod and digital globe imagery to validate that source. And what we find is that because it's an open source, anyone can come to it, data set, is that we can clean up the data set massively from open source sources. And then the last thing we could do is we can actually validate model results. So after we've already created our machine learning model, and after we've already run the model on imagery, what we could do is we could take those results from the model and actually feed that into a Tomnod campaign to see how well our model did. How well did it do marking the cars? How poorly did it do marking the cars? And then we can actually use that data to create a better model, which I'll talk about coming up soon. So how do we actually generate data with Tomnod and Mechanical Turk? So we actually designed Tomnod for Mechanical Turk use. One of the most important things to us is having tons and tons of examples of what these things look like. Your average user has never seen an aircraft from space or a car from space or a truck or whatever we're interested in labeling. So it's important for us to go through the imagery and tag a bunch of different examples. Like one of the things you can see on the top left, that's an aircraft that is dark and almost blends into the ground, but that's something that we want labeled. And then you have your more commonly looking passenger aircraft. Another thing we have built into Tomnod is multiple coverage. So if we're going through a validation campaign and trying to increase the quality of the data set, we don't want one user to be able to say, this is definitely this, and they're the end-all be-all. We actually want multiple users to come in and look at the same aircraft and vote on what they think that aircraft actually is. Is it a small aircraft? Is it a passenger aircraft? And then what we do is we actually take those votes and we feed into what we call our CrowdRank algorithm. So CrowdRank basically takes those votes. It takes things into account like user history, how much experience does the user have, and it actually assigns weights to each user. So if you're a more experienced user, your vote will actually have more weight than others who are maybe newer to the process, and then CrowdRank will actually assign a confidence score to the overall validation of that object. We also use Mechanical Turk qualifications. So Mechanical Turk has a great feature where you can actually set up a bunch of parameters to designate what kind of workers that you want to come to your task or come to Tomnod to label your imagery. So here's the overall process. So what we first do is we create the training data, and then we create the model, and then we run the model over imagery and take those results and validate them. And then what we could do is kind of this loop between validation and recreation, where we have our initial model, we run it over imagery, and we take the results from that model, and we validate them through Tomnod, and we take the good and the bad, and we recreate the model. So here's what the creation process looks like in Tomnod. So what we would do is we call on Mechanical Turk to come to Tomnod and tag a couple cars in here. And Tomnod actually has a pretty cool feature where if you click on a car and a user before you has also clicked on that same car, you'll see a little pop-up saying, you agreed with someone else. And what this does is that it actually trains the user while they're marking cars in Tomnod. So the more time they spend on Tomnod, the better they become just by agreeing with other people. And then after we've created our model and run it on imagery, we actually want to go validate the results of the model. So this box on a car is generated by a computer vision model, and it's a pretty simple validation task. What we want to do is we just want to know, is it a car, is it not a car? Did the model do well, did it do poorly? And then what we could do is we could take the results from the model and actually feed them back into the training process and create a new model from the results of the model. So we could take, let's say it found 5 cars. We have 3 that were correctly marked by the model, and we have 2 that were incorrectly marked by the model. And so we feed both of those in with the tags of good or bad. So it's almost equally as important to feed in good examples as it is bad examples, and so it can learn from its mistakes. All right, so now I'm just going to close it off. So where are we now? We've generated over 1 million labeled objects using this process. And where are we going? We're launching our models as a service, so a customer can come to us with objects of interest, and we can go through the process from start to finish of labeling the data, creating the model, going through that validate, recreate process to create a high-quality model. And how we'll get there, we'll continue to use Tomnod and Amazon Mechanical Turk to generate the data. And just to toot our own horn a little bit, on the left is an image of a car factory with it has about 1,700 cars in the image. And our goal was to take one of our machine learning models that we trained on cars and try to count the amount of cars that are there. And so on the top is Radiant Solutions, which is us. We did pretty well. We got around 1,800 cars. And just to compare that to a competitor algorithm, they were counting at about 2,200 cars. And so the model that you're seeing here, the model results that you're seeing here are from this process that I just talked about. OK, thank you very much. And it looks like we have plenty of time for questions. So does anyone have any questions? Yep.
In the example you showed, like one car marked out of many.
Yeah.
So doesn't that create a lot of the recall? If you use that as a training set, you have very low recall.
One more time?
In the example you showed, there was one car marked out of many.
Yeah.
But if that's a truth set, then the recall is very low.
Right.
If there are many more cars in that, how do you deal with that? Use that as a training set?
Right, so that is an important distinction, is that we want areas to be exhaustively labeled, right? Because what happens is when we feed an image through our training set or training process, and if it's an image that has 5 cars in it, and only 3 out of the 5 cars are actually labeled, what we're actually telling the model is that those 2 cars aren't actually a car. So we need things to be exhaustively labeled. So what we do is in Tomnod is we actually only feed in very small chips of the imagery and not like huge swaths of the imagery. So they have very small areas to focus on and labeled to make sure that the cars are exhaustively labeled. And so then we have the concept of like, do we have to have like a perfectly, like 100% recall, 100% precision accuracy data set? And with this process, you really don't need to have that, because as long as the model can actually just find one car, you can technically just keep iterating over this loop of validate, recreate, and eventually you'll come up with a pretty high quality model. Obviously that will take a long time. If initially you can only find one car, we want it to initially find much more than one car. But that's technically the general overview of how this works. Does that answer your question?
Yeah. Second question.
Yep.
Do you do a separate model for each object class, or do you?
Yeah, it's a good question. So right now we kind of try to do a general model for like a parent category of classes. So we try to do like a road vehicle model, or just a ship model, or a shipping container model. One of the things that we found is that if the objects are of vastly different size, so for a ship model, you can have something as small as a tiny motorboat to as big as a oil tanker. That actually trips up the model a lot. So we kind of go class by class basis to determine, is everything of the same general size? Cars are pretty good because most cars are the same size. And we train models based off size. Now, the overall general picture of what we eventually want to get to is kind of the one model to rule them all. So if you take a look at the concepts of machine learning, if you have a model that can detect cars and can detect trucks, you're actually going to get a higher quality model, because what happens is if you just have a model that detects cars, it's probably going to accidentally also detect trucks, because trucks look extremely similar to cars in satellite imagery. But if you're able to train a model to do both cars and trucks, it's going to actually be able to make the distinction while it's running over the imagery. And if it finds a truck and it's only looking for cars, it knows what a truck looks like and says, okay, this is not a car because I know what a truck looks like. So eventually, what we'd like to have is one massive model that can just do everything on satellite imagery. But we're still kind of in the research and development phase of that portion. Thank you. Any other questions? Yeah.
So the only mention of Amazon I've seen so far is Mechanical Turk.
Yeah.
Did you actually use Amazon Web Services, the cloud?
Yeah. So Tomnod's actually built on Amazon Web Services. So we use EC2 instances to serve Tomnod to the crowd, and we use Amazon's PostgreSQL, so to store the actual markings that come through Tomnod. What else do we use? We actually, so for GPU stuff, we have our own internal GPUs for the training process. But for the actual running over the imagery process, we do use Amazon's GPUs. So if you recently saw at the keynotes, there's the P3 instances, which are pretty powerful GPUs, and we need those pretty powerful GPUs to run over the wide swath of imageries that we have. Thanks. Any questions? Yep.
I guess I was wondering, do you have a mobile app for Mechanical Turk so that people can work more, intermittent?
So a mobile app for Tomnod?
Yeah.
Okay. To come, yeah. We've definitely talked about that before. It would be pretty cool to just kind of like a Google Map app where you can just kind of scroll through a bunch of satellite imagery and just tag things and things like that. The actual implications of trying to serve massive amounts of imagery to people, it's a little bit tougher, but that's definitely something we've taken to consideration and are working on. Yep.
How detailed can the models get from space? Like, for example, can you identify individual people? Can you identify types of cars? But not just a car. Can you say it's a 2000 Honda Accord?
Right.
How detailed can we get?
So our satellites take imagery at 30 centimeter resolution, which means that when you look at the pixel in the actual image, it represents 30 centimeters on the ground, which sounds pretty close, but we cannot look at people's license plates or identify people from space or determine that extreme detail in cars. Right now, with the resolution that we have, we can determine the difference between a small car and maybe a slightly larger car, or a small car and a truck, things like that. Thanks. Yep.
Are you doing anything with
A great question. So our satellites don't always take perfect imagery straight down on the Earth. And what happens sometimes is that if we have a satellite coming over the Earth and we have an area of interest that's slightly off of its orbital path, what we do is we kind of bend the satellite's camera a little bit to point towards the area that we're interested in. And what that does is it creates what's called an off-nadir image. So it's a slightly shifted image. So what you'll see is almost like a 3D representation of the image that you take. So when we're training our machine learning models, we have to keep that in mind. So when we're serving the imagery to the crowd, we want to make sure that we have a diverse set of everything from the biggest naders that we have to straight on nadir. Thank you. Yep. That's just mostly just writing good code, just being able to supervise the model as it gets trained. And when we create these training sets, it's not all used for training. We split it up into train and test sets. So as we're retraining the model, as we do that recreate process, we're able to see in real time how is the accuracy of our model increasing or decreasing. And if we see overtraining, what will happen is our precision will go down because now we're marking things that are not cars in the ground truth data set. Thank you. Yeah.
Assume you're training for cars. Roughly how many pictures do you need to make a good model?
So it's really not. So it's a factor of two things. So it's really not how many pictures we have, but it's actually how many labeled cars do we have, right? So in this model here, it's around 300,000 cars labeled in satellite imagery, and it's important to have a geographically diverse set of images too, right? So we want to make sure that we're marking cars in South America, in Africa, in China, in North America, all the different kind of geographic regions. And then we also want seasonality in there as well. So we want to have cars marked in the winter. We want to have cars marked in the summer, spring. And because things are just going to look different in those seasons and in those geographic regions based on the time of year and things like that. So we can have, one model that can detect all cars in all geographies and all seasonalities. Yeah.
One of the things you mentioned was classifying the region that you're in. You're pretty comfortable with that at that point? Because that seems to be an assumption.
Yeah.
Where it's located.
Yeah. So we're kind of following the general trend of machine learning and imagery, where classification is a very, at an advanced state in ground imagery, where you're able to take a picture and just generally classify the entire picture as this is a beach or something like that. So with satellites, what we do is we have that same application. Machine learning has come to a state where it is pretty much an assumption that you can train a pretty easy machine learning model on just classifying what type of land something is. So if you guys are looking into getting into machine learning on satellite imagery, it's a good starting point to get to because you can get good results fast from it. But it was kind of just like our stepping stone, learning the overall process of classifying and then moving on to detectors, which is much harder. Any other questions? Okay, thanks very much.